Hello Professor, my name is Janil Rana. Today I will present my secure file transfer project built to reliably transmit massive payloads such as 4 GB file across a fully untrusted public internet link. Our threat model assumes an active man-in-the-middle capable of intercepting, reordering, dropping and replaying packets. To guarantee confidentiality, integrity, authenticity and availability, I designed two distinct architectures that meaningfully diverge across various dimensions. The first approach operates at the transport layer. It relies on streaming Mutual TLS 1.3 to encapsulate the standard TCP string using hardware accelerated record encryption. And the second approach operates directly on the application layer. It builds custom independently encrypted envelopes using long-term ED25519 identity keys for peer authentication and ephemeral key agreements for forward secrecy, and a granular chunk level AED wrapping. This decoupled design allows payloads to safely route through untrusted intermediate proxies or storage brokers without exposing the plain text. So here I have launched my interactive evaluation suite. Step 1 provisions are cryptographic root of trust, that is pre-generating X.509 certificates and the keys. Step 2 dynamically builds a random payload and prints its whole file SHA-256 digest to serve as our absolute integrity baseline. Then the step 3 begins approach A. So on the screen the client initiates an mTLS handshake over TCP loopback. Authenticity is strictly guaranteed. The server enforces SSL certificate requirement to authenticate the client, while the client performs strict subject alternative name validation against the server certificate. This completely neutralizes endpoint spoofing attacks. Once established, the file streams using pre-allocated 1 MB sliding window buffers. This satisfies our memory constraint requirements, preventing RAM saturations even on large runs. Confidentiality and stream integrity are protected by TLS AES 256 cipher shoot. Upon socket completion, the receiver validates the whole file plaintext SHA-256 hash before officially saving the artifact, running at speeds exceeding 500 MB per second. So let's examine approach B, where security is applied before data ever hits the socket. Notice phase 1, the handshake protocol. To authenticate without exposing identity keys to wire interception, both parties generate single-use ephemeral keypairs and sign their peers' ephemeral keys using the pre-shared ED25519 private keys. This achieves absolute mutual authentication. So when we extract a forward secret 256-bit session key, if an attacker compromises long-term keys in the feature, past captured session remains mathematically unbreakable. In phase 2, the sender transmits encrypted metadata containing the file name, total chunk count, and a cryptographically secure 16-byte random session ID. In phase 3, the payload streams. Every single 1 MB chunk is encapsulated in its own AES 256 GCM envelope. To prevent reordering and replay attacks, we bind a strict monotonic counter derived directly from the chunk index along with associated authenticated data. If an active attacker injects or reorders bytes, the receiver's AED tag verification instantly traps the manipulation and aborts the transfer. Now let's demonstrate our stretch goals. Resumable transfers using signed chunk offset under approach B. Here a dedicated 500 MB file transfer starts streaming. Suddenly I simulate a catastrophic link failure by terminating the sender's process mid-flight. Rather than corrupting the file, the receiver catches the socket exception, safely flushes the partial temporary data to the disk and persists a lightweight .resume JSON state, recording that exactly 103 chunks were successfully ingested. Watch what happens when a fresh receiver process is launched to recover the dead session. Phase 2.5 transparently detects the existing .resume trackers to guarantee end-to-end integrity without loading the partial file into the memory. It rapidly streams and rehashes the existing 103 MB of data in a fraction of a second to restore the SHA-256 context. It then transmits an encrypted reassumption request specifying the exact block offset, and the sender seeks precisely to that file pointer and streams only the remaining 379 blocks. The whole file hash perfectly matches our plaintext source. So this completes my deep dive demonstration, and thank you for your time.